By 2050, electric vehicles could eliminate over 1.5 gigatons of carbon dioxide from the atmosphere every single year. That is roughly the same as wiping the entire carbon footprint of Russia off the map annually. But here is the part that almost nobody talks about: the process of building that electric vehicle might already be destroying the planet before you ever plug it in. Welcome to AutoVision Daily. Today we are pulling back the curtain on the full environmental story of electric vehicles, not just the clean tailpipe narrative you have heard 1,000 times, but the mines, the grids, the batteries, and the brutal trade-offs that come with the so-called green revolution. We will walk you through where EVs genuinely win, where they quietly lose, and the one truth about battery production that the industry has been downplaying for years. If you think you already know how green your electric car really is, stay with us, because the answer is far more complicated than the brochure ever told you. To understand the real environmental impact of electric vehicles, you have to go back to the beginning. Not the beginning of EVs, but the beginning of the climate crisis conversation itself. In the 1970s and 1980s, scientists and policymakers began recognizing that transportation was one of the most significant contributors to greenhouse gas emissions globally. By the early 1990s, California passed some of the world's first zero-emission vehicle mandates, pushing automakers to explore alternatives to the internal combustion engine. Early electric vehicles like the GM EV1 appeared in the late 1990s, but they were limited by range and infrastructure. The modern EV revolution truly began in 2008 when Tesla introduced the Roadster, demonstrating that electric cars could be both high-performance and desirable. Since then, adoption has accelerated dramatically. In 2023 alone, over 14 million electric vehicles were sold worldwide, bringing the global EV fleet past 40 million units. The ambition is enormous, and so is the environmental bet being placed on this technology. Transportation accounts for approximately 16% of all global greenhouse gas emissions. In countries like the United States, that figure climbs to around 27%, making it the single largest source of emissions nationally. Within that category, passenger cars and light trucks are responsible for the majority of the damage. This is the core problem that EVs are designed to solve. And when you look at the operational phase of an electric vehicle, meaning the miles actually driven, the data is genuinely impressive. A typical battery electric vehicle produces zero direct tailpipe emissions. Over its operational lifetime, depending on the electricity grid it charges from, an EV can reduce carbon emissions by 50 to 70% compared to a gasoline-powered vehicle. In countries with very clean energy grids like Norway, France, or Sweden, that reduction climbs above 80%. Even in countries with dirtier grids heavily dependent on coal, EVs still come out ahead on life cycle emissions in most studies. The Union of Concerned Scientists found that in virtually every region of the United States, driving an EV produces fewer emissions than driving a comparable gasoline vehicle. That is a powerful finding, and it matters enormously. But here is what nobody talks about in the glossy EV commercials. Before an electric vehicle moves a single inch down the road, it has already generated a substantial carbon debt. Manufacturing an EV, particularly its battery pack, is an extraordinarily energy-intensive process. Producing a large lithium-ion battery pack, roughly 75 to 100 kilowatt-hours, which is standard for many modern EVs, generates somewhere between 8 and 20 metric tons of carbon dioxide equivalent during manufacturing alone. Compare that to producing a conventional gasoline vehicle, which generates roughly 6 to 10 metric tons during manufacturing. The EV starts its life with a significant carbon disadvantage, sometimes called the manufacturing carbon debt or the carbon backpack. This does not mean EVs are worse overall, it means that the environmental advantage only emerges after a certain number of miles driven, a threshold often called the break-even point. Depending on the grid and the battery size, that break-even point typically falls somewhere between 15,000 and 50,000 miles of driving. For most drivers who put roughly 12,000 to 15,000 miles on their car annually, the break-even arrives within the first 2 to 4 years of ownership. Now let us talk about the part of this story that goes deepest underground, literally. The batteries powering electric vehicles require lithium, cobalt, nickel, and manganese. Mining these materials is where some of the most serious environmental concerns surrounding EVs are concentrated. Lithium extraction, particularly in the Atacama Desert region of South America spanning Chile, Bolivia, and Argentina, a region known as the Lithium Triangle, consumes enormous quantities of fresh water in one of the driest places on Earth. Estimates suggest that producing 1 metric ton of lithium requires approximately 2.2 million liters of water. Local indigenous communities and ecosystems have raised serious concerns about water table depletion, soil contamination, and disruption of fragile high-altitude wetlands. Cobalt mining, concentrated heavily in the Democratic Republic of Congo, carries its own catastrophic baggage, including environmental degradation, toxic runoff into rivers, and deeply troubling human rights conditions. Nickel refining in countries like Indonesia and Russia has historically produced sulfur dioxide emissions and created dead zones in surrounding waterways. These are not fringe concerns or anti-EV talking points. They are documented realities that the industry must confront head-on. The good news is that the industry is confronting them, even if slowly. Battery chemistry is evolving rapidly. Lithium iron phosphate batteries, known as LFP batteries, are gaining significant market share because they require no cobalt at all and use far more abundant materials. Tesla now uses LFP chemistry in its standard range vehicles. Companies like CATL and BYD have made LFP their dominant chemistry globally. Solid-state batteries, which promise higher energy density with potentially less reliance on problematic materials, are moving closer to commercialization, with Toyota and several startups targeting production by the late 2020s. Direct lithium extraction technology, which can recover lithium from brine with significantly less water consumption than conventional evaporation ponds, is being piloted in multiple locations. These advances are not theoretical, they represent concrete progress toward reducing the upstream environmental damage caused by EV production. There is another dimension to the environmental equation that deserves serious attention, and that is the electricity grid itself. An electric vehicle is only as clean as the electricity that powers it. This point cannot be overstated. If you charge your EV in a region powered primarily by coal-fired electricity, your effective emissions per mile are higher than in a region powered by renewables or nuclear energy. In 2023, approximately 40% of global electricity generation still came from coal. However, the critical insight here is that grids are getting cleaner every year. As renewable energy capacity expands, and solar and wind are currently the fastest growing sources of new electricity generation worldwide, every electric vehicle on the road automatically gets cleaner over time without any modification whatsoever. A gasoline vehicle, by contrast, is locked into its emissions profile from the moment it rolls off the assembly line. That asymmetry is one of the most underappreciated advantages of electrification as a long-term strategy. Then there is the question of end-of-life battery disposal, which is the environmental chapter that still needs to be written more carefully. Lithium-ion batteries contain toxic chemicals and heavy metals that require careful handling at the end of their useful life. However, battery recycling technology is advancing quickly. Companies like Redwood Materials, founded by former Tesla CTO J.B. Straubel, are building industrial-scale battery recycling operations capable of recovering over 95% of the critical materials from spent battery packs. Li-Cycle, Umicore, and several other firms are scaling similar processes in Europe and Asia. The vision of a closed-loop battery economy where materials are continuously recovered and reused is becoming increasingly viable, which would dramatically reduce the need for new mining over time. What does all of this mean when you step back and look at the full picture? Electric vehicles are not perfect. They carry real environmental costs associated with manufacturing, mining, and the current state of electricity generation. These costs are legitimate and worth taking seriously. But the trajectory is unmistakably in the right direction.